No one has ever seen this giant isopod eat a single piece of food, not during the day, not during the night, and actually not even once in the past 1,758 days. And yet this giant isopod is still alive, still moving, and the only animal in the world that is living off 0 calories. These things will not die. If you take any other deep sea creature and bring it to the surface, they'll explode immediately from the pressure change. But when giant isopods were brought to the surface from over 2,000 m below, they still did not die. Why are these animals so horrendously resilient? Why would they bother to evolve to be able to survive the surface if that's not even where they live? And what things will actually kill them? To understand why these things are so hard to kill, we first have to understand what they actually are. And the answer is they're bugs. Well, sort of. If you go into your backyard right now and flip over a damp rock, you'll probably find this little gray ball that rolls up when you poke it. That's a pill bug. This is a giant isopod, and genetically they're basically the exact same animal. Just this one is 60,000 times heavier and lives in the bottom of the ocean. They share the same film, subfilm, class, and order isopod, but this doesn't explain why giant isopods evolved to be so much more just indestructible. If you stop feeding a garden pill bug, it's going to dry out and die in about 2 months. Most humans can only go about a few weeks without food before it's over. And logically, this makes sense. The bigger you are, the more fuel you need to keep going. A blue whale needs to eat millions of calories a day just to exist. A semi-truck needs more gas than a moped. So, have giant isopods figured out how to break the laws of thermodynamics? Well, not exactly. By all rights, an animal this large or, well, giant should starve to death in latest a few months. But because they live in the pitch-black, freezing void of the deep ocean, food doesn't exactly grow on trees. It barely exists at all. Compare this to the normal tiny pill bugs where they live. Food does actually grow on trees. Evolution didn't push the pill bugs to be able to starve for years, since there was always a way higher abundance of food available. When food is much less predictable so far below, you need the ability to starve or else you're cooked. But saying evolution made them need to be able to not eat doesn't actually explain how they're able to not eat. This is still breaking the laws of thermodynamics. Even just existing burns thousands of calories for people. It doesn't matter if you're bedrotting all day, you need food. Giant isopods are ectotherms, meaning their body temperature is barely above freezing. They waste 0 energy on heating themselves up. Its metabolism is so absurdly slow that it borders on suspended animation. Its cells are doing the absolute bare minimum required to qualify as alive. They also rarely are making any noticeable movements. So they're essentially permanently bedrotting in an even more relaxed state. But having a slow metabolism is only half the battle. You still need some amount of energy, and this is where their second trick comes in. When a food source does finally drop from above, usually in the form of a massive dead whale carcass, the giant isopod doesn't just eat until it's full. It eats until it is physically disabled. These things have been observed gorging themselves so hard that their rigid exoskeleton actually restricts them from moving, and their legs can no longer lift their bellies off the seafloor. They turn into immobile meat-filled rocks. They pack this food away into massive lipid reserves in their liver, essentially biological battery packs that are so energy-dense that they can slowly sip on them for years. It's the same idea of if you got stranded on an island, being overweight is an advantage, since you have more energy stores to last longer, but just to a really weird extreme. And this isn't just a theory, because we actually watched this exact scenario play out in real time with the most famous isopod in history, number 1. I know that sounds like some special name, but number 1 wasn't actually a nickname like the chosen one. You were the chosen one. It was just the ID tag the aquarium gave him as the first Bartholomew specimen. It stuck after that. This guy was a resident of the Tober Aquarium in Japan, and in 2009 he decided to feast. He absolutely demolished a whole horse mackerel, hacking those lipid reserves to the absolute brim, and then he just decided he was done. For the next 5 years, the keepers would try to feed him. Every single month, they'd wave mackerel in his face, drop squid near him, basically begging him to eat. And every single time, number 1 would just sniff it, maybe poke it with a leg, and then just walk away. He treated food like it was invisible. He didn't eat a single bite for over 1,800 days, and then he died. So, when he finally died in 2014, the autopsy revealed something insane. He didn't die of starvation. His body wasn't empty. He seemingly just died of old age. He had eaten so much in that one sitting in 2009 that he was still running off the battery power of a meal he ate while Obama was in his first year of presidency, and he was still able to go longer. Whether it was factors from not being in his natural environment, just dealing with old age complications, or stress from being seen by so many people, something eventually killed it. But it likely wasn't the lack of food. He was still chilling, but honestly the fact he was even alive in that tank to begin with is a miracle in itself. Remember, number 1 wasn't in the deep sea anymore. He was at surface level, and for almost any other creature from the abyss, being dragged up that fast is literally a death sentence. If you bring a blobfish up to the surface, it turns into a blob. If you bring a deep-sea rockfish up, its eyes pop out, and its stomach gets pushed out of its mouth. It's gruesome. It's the same reason why giant kraken attacks from giant squids don't really happen. If you ever see one at the surface, it means it's dying. Definitely not trying to capsize your boat. This happens because the gas inside their bodies expands rapidly as the pressure drops. It's the same physics that make a soda can explode if you shake it and open it. The pressure is giving their body support that they don't have, which is why almost no deep-sea creatures have any sort of strong skeleton or connective tissue. Remove that pressure and it's the same animal but without a skeleton. And for any animal on the surface that does have a skeleton, that would be brutal. So, how can the giant isopod survive being dragged up from 2000 m down without turning into a pile of goo? Because it's built different, literally. Unlike most fish, giant isopods don't have swim bladders. Those gas-filled sacs that fish use to float, they are benthic roars, meaning they are designed to walk on the floor, not float. No gas. Sacs means no expanding gas, which means no exploding bug. But also their exoskeleton is an absolute unit of engineering. It's arranged in these overlapping segmented plates that allow it to curl up into a ball to protect its soft underbelly. This armor is designed to withstand the weight of 2,500 m of water. But because it's so rigid and not filled with pressurized gas, it holds its shape perfectly fine at sea level. 2. It's basically wearing a suit of armor that works just as well in space as it does in a submarine. So they don't starve and they don't explode, but there is something that can kill them. And honestly, it's kind of embarrassing because while they are immune to the crushing depths of the ocean and starvation, they aren't immune to themselves. Giant isopods aren't exactly the smartest creatures in the deep. Thinking requires too much energy. They are scavengers, and when a large food source drops, like an alligator carcass in a science experiment, they swarm it, all dog piling on or isopod piling on, and in the frenzy to eat, they often mistake each other for the food. They don't have great vision. They just bite whatever feels like meat. Luckily, because their armor is so thick, these accidental munches usually just result in a very confused isopod, rather than a dead one. Giant isopods do have actual predators, though. Sharks tear into anything on the seafloor, and in the chaos of a feeding frenzy, an isopod can get chomped right through its shell. Octopuses are a bit more strategic, and they can grab an isopod, pry at the shell, and bite the inside with their beak. But there's one massive elephant or massive isopod in the room. Why would they bother getting this big? Wouldn't it just attract more attention from predators? Well, while they are a case of deep-sea gigantism, their reasons aren't all the same as things like giant squids. Yes, being big does actually make giant isopods a bigger target to things like sharks, but predators aren't actually that common in the sea. Even if deep-sea sharks will go after them, they just aren't common enough to counteract the other benefits of being massive. And what are these? When they're scavenging, being big lets them hold their position on the carcass and tear bigger chunks. And the biggest benefit is there is literally more isopod to stuff food into. If a whale suddenly falls and you're about to get your meal for the next 5 years, you want to stuff your face as much as possible. Also, if a whale falls, you actually need to reach it too. These events aren't insanely common, and the ocean is massive. A dead whale falls, but it's 5 mi away on your tiny little legs. That walk would take weeks. You would literally burn more calories walking to the food than the food would give you. You'd die of exhaustion halfway there. But by being giant, you can actually cross the ocean floor with massive strides for essentially the only time you'd ever need move. And once you're there, you can claim what you need and then dip. It's honestly kind of weird when you think about it, because no other isopods in the world got anywhere near as big as this. Almost all terrestrial isopods are barely an inch at most. Even Antarctic isopods that got bigger from polar gigantism only reach about 5 inches. Other large ones like members from Cerulolus and Glyonidus can only reach up to 3 in as well. Beyond that, the rest of the world's isopods stay firmly in the small to tiny range, making the deep-sea Bartholomew line the only group that ever pushed into truly giant sizes, nearly triple the second largest isopod line. Functionally, this isopod shape shouldn't be designed for getting to large sizes. The flattened body, simple gill system, and tough armor all impose natural limits that keep almost every lineage small. Honestly, no one would even have questioned if giant isopods didn't exist. We would just assume that the isopod build was designed for staying small. That armor system wouldn't be expected to fit on a larger body. Unfortunately, this also reveals one of the isopods' only weaknesses. Because they are wearing a suit of armor, they can't just grow. The armor doesn't stretch. So they do the well-known process called molting. But for the giant isopod, it's a nightmare. Molting takes a ton of energy, and giant isopods prefer just bedrotting on the ocean floor all day. And when their armor is off, it leaves them soft and squishy while the new shell hardens. If a predator finds them during a mole, they're basically a soft shell crab, special at a seafood buffet. So they come up with a genius strategy. They don't molt all at once. They do it in halves. First, they shed the back half of their armor, wait for it to harden, and then shed the front half. This means that At any given point, they still have at least 50% of their armor active and ready to defend themselves. It looks absolutely ridiculous, like they're wearing pants but no shirt, or a shirt with no pants, but it helps them get through the stage. But out of all the things these guys are able to survive, there's one thing they absolutely cannot survive, and it's the one weakness that completely unravels their entire survival strategy: warm water. These guys are able to survive thousands of pounds of pressure, living in less than 4 degrees Celsius, starving for years, and they can even survive outer water for over an hour, and a slightly lukewarm bath will kill them. Sudden warmth will cause instant metabolic overload. Oxygen demand will spike, enzymes will miss fire, and it will kill them almost instantly. For all the ridiculous things they can endure, this is the kryptonite of the giant isopods. They're one of the most unique creatures in the world, one of the most highly adaptable, but animals' biology can only be good at so many things. It's not every day you can see an animal survive out of its natural habitat, but something tells me, especially in the case of number one, he didn't want to leave in the first place. Thank you for watching. If you guys want to see a video about why worms become terrifying when they enter a different habitat, check it out here. And until, what makes giant isopods even more unsettling is not just what they can survive, but how little they seem to care about surviving at all. These animals do not hunt. They do not chase. They do not plan. They wait. Their entire existence is built around patience on a scale that almost no other complex animal can match. In the deep sea, waiting is not a passive act. It is a strategy. Giant isopods may go months or years without encountering a meaningful food source, but when one finally appears, speed matters. Despite their sluggish reputation, they are capable of sudden bursts of movement. Chemical sensors along their antennae can detect decaying flesh from astonishing distances. A whale full kilometers away becomes, to them, an irresistible signal drifting slowly through the water. Once an isopod reaches a carcass, competition begins immediately, not just with other scavengers, but with its own species. Giant isopods do not cooperate. There is no hierarchy, no sharing, no restraint. The first instinct is to eat as much as physically possible, as quickly as possible, because there is no guarantee another opportunity will ever come. This extreme feast or famine lifestyle has shaped nearly every part of their biology. Their digestive system is oversized relative to their body, capable of processing enormous volumes of food in a short time. Their stomach can stretch dramatically, and their internal organs compress to make room. After feeding, their movement slows even further, sometimes to the point where they appear almost lifeless, conserving every possible unit of energy. Their lifespan is another mystery. Because they grow slowly and molt infrequently, estimating age is difficult. Some researchers believe large individuals may live for several decades. Others suspect even longer lifespans are possible in the stable conditions of the deep sea, where temperature, light, and seasonal change barely exist. In such an environment, aging itself may proceed differently. Reproduction in giant isopods is equally slow and deliberate. Females carry fertilized eggs in a brood pouch called a marsupium, similar to terrestrial isopods. But unlike many marine animals that release thousands of eggs into the water, giant isopods invest heavily in fewer offspring. The young hatch as fully formed miniature versions of the adults, already armored and ready to survive on their own. There is no larval stage drifting helplessly in the water column. This reproductive strategy makes sense in a world where food is rare and unpredictable. Producing fewer, more resilient offspring increases the chance that at least some will survive long enough to encounter a major food fall. But it also means population recovery is slow. If numbers decline, it can take many years for them to rebound. This vulnerability becomes important when humans enter the equation. While giant isopods are not commercially fished on a large scale, they are frequently caught as bycatch in deep-sea trawling operations. When brought to the surface unintentionally, many survive the pressure change, only to die later due to temperature shock or prolonged exposure. As deep-sea exploration and mining expand, their habitat faces disturbances it has never encountered before. The deep ocean was once considered too remote to be meaningfully impacted by human activity. That assumption is no longer true. Noise pollution, sediment plumes, chemical runoff, and climate-driven temperature changes are reaching even the abyssal zones. For an animal adapted to near-perfect environmental stability, even small changes can have outsized effects. Temperature, in particular, is a looming threat. As deep waters slowly warm, metabolic rates increase. An animal built to survive by doing almost nothing suddenly finds itself burning energy faster than its entire survival strategy allows. Unlike surface species, giant isopods cannot simply migrate to cooler regions easily. Their movement is slow, their range limited,